Ah, never heard that before. And now I'm going to go here. And so the topic for today is hash functions. And it's kind of hard to get as far as we have in the course on cryptography without talking about hash functions. I kind of feel like this should be one of the first topics discussed, but anyway, here it comes now. And so a hash function, it takes an arbitrarily long input, like it could be the smallest file on your computer, like an empty file, or it could be your entire hard drive or some gigantic movie or something, and it reduces it to a fixed length fingerprint. So it's a fixed length digest of a message, of arbitrarily long message. That means as long as you want. And this has tons of applications. Some of them we'll go through here. Like it's important in digital signatures. We've shown that actually in the PSS padding, a hash function was used, and then hash functions were also used in optimal asymmetric encryption padding. So we've already mentioned hashing in those contexts. So it's important in digital signatures, and it's more than just the padding thing, as we'll see in a second. So one of the reasons we did padding was to stop forgeries, but there's kind of a worse issue that we'll explain in just one second. Hash functions are used often in key derivation. You guys have ever heard of, you might have noticed that I have gotten out of it, but I used to be a pretty big cryptocurrency nerd. And there are things called wallet words. Does anybody know what those are?
Like a password?
Yeah, it's 10 or 20 words that are all taken from a very simple dictionary that I think has 2,000 entries. And it's words that everybody knows, like horse, water, table, blah, blah, blah. So what you can do is randomly generate a choice of 10 words in a prescribed order from this word list. So that has pretty high entropy. So how many possibilities are there? It's like 2,000 to the 10th power, which is a pretty big number. That's like, yeah, much better than a password. And then you can remember those wallet words. You could even theoretically memorize them. And then you pass them through a key derivation function, which is kind of like a hash function. And that specifies a unique cryptographic key. So let's say, 256-bit key or whatever key you need. And that would be your private key that lets you spend the cryptocurrency or whatever else. Also used a lot in password storage. I thought about showing you guys my shadow file, but then I decided that would be a bad idea because I'm going to put this video on the internet. But you might know that, like, when you log on to a server, the server doesn't actually store your password. It stores a hash of your password. So when you type in your password, it hashes it and then compares that to what it has on file. And the advantage to doing that is then the server doesn't have a file on it that has like everybody's password, unless the IT people are completely incompetent, which happens from time to time. Message authentication codes, which we haven't talked about yet. And also just detecting file changes. So it's often used in computer forensics. If you hash a file and then you change it in the slightest way, and then hash it again, the hash will be completely different. Okay, so now let's go over some motivation relating to digital signatures here, and I'm just going through the way the textbook presents this material. So here's some motivation for why we need hash functions. And the example is signing long messages. So let's, we've been doing these examples of digital signatures where everything that we wanted to sign was in ZN. And so that means it's like less than 2048 bits or something. But obviously we might want to sign a file that is much bigger than that. Like even a lot of word processor files are bigger than that. So what do you do in that case? So in that case, you kind of naturally would have sort of blocks of message, just the same way that we did when we talked about block ciphers, except now we don't want to encrypt the file, we want to sign the file. So how are you going to sign a file that takes up several different 2048 blocks or whatever? So the most obvious thing is to just sign each one. So sign this one, sign that one, sign this one, and sign this one. And then you get 4 signatures here, S1, S2, S3, and S4. Just writing this down, you can see that it's clunky. It has like several problems here. One is that this is going to be very slow. You could easily have thousands of these blocks, and signing takes, do you remember with the 15,000-bit RSA key? My pretty fast computer can only do 6 signatures per second. So what if I wanted to sign, like a movie or something? It would take the rest of my life. So just the speed of doing this is bad. And also this creates a lot of, a huge signature file. So the signature file is big as the thing that you're going to sign. So this is kind of ridiculous. If you're going to sign a 6 gigabyte movie, then the signature is also going to be 6 gigabytes. You don't want that to be true. And then another problem is security issues. So somebody is gonna verify the signature at some point later. So how are they going to verify it? So it just seems like they're going to sort of verify these one by one, or that's the most obvious thing anyway. It's just to verify each one, and then if they all verify, then you say that the message is that the signature is valid. But look, Oscar or Eve or whoever can rearrange these blocks or even just remove some of them, and then the validator will think that the signature is valid, but it's not what you sent. It's been adulterated by the person in the middle. Okay, so 3 big problems here. So instead of doing all that, you can just sign a hash of the message. And that's basically what PSS is. PSS also includes some salt for randomization, but it's basically just a fancy way of hashing a message and then signing it. So you put the message through a hash function. So often people use this sort of icon to talk about a hash function because it has big inputs but small outputs. So h of x comes out, the hash of x. So this is some fixed number of bits depending on the hash function. Like the most commonly used hash function is probably SHA-256 that has a 256-bit output. So now you can imagine this being just like 256 bits. And now you would sign this. So put this through the signature algorithm. And that requires some kind of private key. And then what comes out is a signature. So once Alice produces that, she can transmit to Bob or whoever the message and then the signature. And then when it's Bob's time to verify, he can just he can use the signature. I mean, he can use the hash algorithm as well as you can. So in the verification, he just takes x and he computes h of x, and then he can take h of x, which is the hash of the message, and the signature that you sent, and then just do ordinary verification. So this would just be the verification algorithm that he would use for this signature algorithm, the same way we presented it in the last time. And then so he attempts to verify the signature, and he accepts or rejects, depending on whether or not the signature is valid. Okay, so that solves a lot of problems. So we can see already there are 6 desired properties of hash functions that we will go over. But now let's just list three of them. Desired properties. So one is you want to be able to hash a message of any size. So in practice, some algorithms do have limits, like the file can't be more than like 2 to the 80 bits or something ridiculous like that, but it's so big that it's not really a problem. Another desired property is that this has to happen quickly. And a third thing is that you want a fixed length output. And a fourth thing is you want the hash to have sensitive dependence on the input. So we'll say a lot more about this last one here. Let's just give some examples using the terminal. Okay, so I'll share a terminal window here if I can find one. Here's one. Oh, okay. So there I printed my shadow file to the screen, but if you have a Linux system, here it is. If you want to look at your own shadow file, it's just it's in etc. shadow, and you have to enter the super user password in order to be able to look at it. Here are some commonly used hash functions. So here's SHA-256, SHA-512. So this family is something called SHA-2. So that's secure hash algorithm 2. There's also SHA-1. I guess that's what this is. So here's SHA-1. SHA-1 is broken. So you definitely shouldn't use that one for any application. There are also some older hash functions like MD5. So if you want to use these, like this will be hashed by MD5. And so I'll type Control D here, and I get this hash digest. And I think that is 160. It's 160, 2, 4, 6, 8, 10, 12, 14, 16. So it's 16. It looks like it's 16 bytes times 2, so that's 32 bytes. So what is 32 times 8? 256? That's not right. I'm sorry, I'm an idiot. I should know that. So let me do an example of a SHA-256 hash. Hello, name is blah blah. So that's a 256-bit hash. So this one is half as long. So that's 128-bit hash from MD5. MD5 is still used commonly as like to produce check digits. Like after you download a file, you can tell if it's been accidentally modified in transit by taking its MD5. So it's only good for accidental modifications, though. It's no longer good for detecting malicious modifications. so there are speed issues. So let me go into my documents folder. And I ran an OpenSSL speed test on all of the, whoops, okay, I already have that open in a different window, so I'll just share that one. Where is that one? Right here. Okay. So if you just run OpenSSL speed, this tells you how quickly all the things in the OpenSSL library run on your machine. So not all of these are hash functions, but MD5 and MD4. MD4 is a predecessor of MD5. You can see that it is very fast. What it's doing here is it's hashing files of different sizes. So the files range from 16 bytes to 16,000 bytes. And this is how many hashes can be performed in 3 seconds. Yeah, so does this make sense? This is 116,000, but this is millions. So it's interesting that the numbers are in thousands of bytes per second processed. So I thought I knew what this output meant, but I don't know why numbers are in quotes here. So it definitely only allowed itself 3 seconds each time. But I think this might be the rate. So this number must be
Kilobytes?
Yeah,
Per
it's
second?
megabytes per second. Yeah, it's megabytes per second. Thank you. So this is 1,000,000 megabytes per second. So that's like a gigabyte per second. So that's very, very fast.
Wait, isn't the K?
Oh yeah, and then it's even more than that. So it's, but oh yeah. So I think that it can't be that big though. So I think we should ignore the K. And I think this 1,000 here is just telling us about the K being there.
It says bytes per second.
Yeah.
So like 1,000,000 bytes is like how many megabytes?
But here it says 1,000 bytes. So let's just call it megabytes because that's shoot, that's kilobytes. You might be right. Yeah. So then you take kilobytes and you multiply it by another 1,000 and you get megabytes. And that's about right. Thanks, Aiden. Okay. So this is like 1.4 gigabytes per second for this MD5. And then here's SHA-1, and it's a little bit faster than MD5. I think this is ripe. Is this ripe MD? So there's this kind of weird hash function ripe MD that was made by Europeans instead of Americans. So if you think that all the American standards are backdoored, then you can use the European version instead, or you could use some combination. Here is, down here is SHA-256, and here's SHA-512. So those are commonly used hashes. They're about half as fast as MD5 and SHA-1, but they're actually secure. So you know, if you just need an out-of-the-box hash function, then SHA-256 is a good choice. Okay, so let's quit this and let's talk about the or come back to the notebook anyway. All right. Oh, and sorry, we did all this, but I didn't talk about sensitive dependence on the input. So let's come back to the terminal, and I just want to, let me quit this. So I'll do SHA-256 again. Let's do it like this. So echo, I am a bunny rabbit, SHA-256 sum. Okay. So that is a kind of like a pseudo random number. If you change this in the slightest bit, quite literally, like if I change this A to a B, I believe that's a 1-bit difference. But the every bit in the digest flips with probability 50%. So you get something that's completely unrelated. Okay, so quit this. Come back here. All right, and obviously they all have fixed length output. Most of them tell you how many bits the output is in the name, and they're all pretty fast. Okay. So now let's talk about the security. Those are just the performance properties, but what are sort of the security properties? So we talked about this, the way you can combine hashes with signing. Let's say that Bob wants to send Alice a signed message X. So what does he do? He makes S, and S is just the signature algorithm with his private key applied to the hash of the message that he wants to send. And then he sends this along, and here's X and S, and dun dun dun. Here's somebody in the middle. You call them Mallory or Oscar or Eve or something. So Mallory is able to take X, and she can also compute H of X, so she knows what that is too. And maybe using these two things, she might be able to create, using some kind of process, some other message X1. And so X1 is not the same as X, but it does have the same hash. So suppose that she can do this. She can find some new message that has the same hash as X. So we call this like a second preimage. That's would be this thing. So you have X, which is the input, and H of X is the image, and then X is a preimage of the hash. So what Mallory has been able to do here is create a second preimage. So a second input that gets hashed to the same value. So if she's able to do this, it breaks the signature scheme, because now she can send along, instead of X, she sends X1 and S. And then when this gets to Alice, what will Alice do? Alice will try to verify the hash of X1 and S, but this will just be exactly the same as what she would get if she tried to verify H of X and S. And because S is a legitimate signature of X, this will be accept. Okay, so you've just created a forgery and fooled Alice. And the thing that went wrong here is that Mallory was able to compute this second preimage. So this is an example of a second preimage attack. So given X and H of X produce X1, which is not equal to X, such that the hash of X1 is equal to the hash of X. Okay, so this is our first desired property of a hash function, is that hash functions should have second preimage resistance. That means it's difficult or impossible to produce a second preimage. So let's think about this for a second. Let me come back here to the terminal, and let me just hash something like let me do SHA-256 of Tesla, whatever that is. Whoops, some Tesla. Oh, it's a directory. Okay. So how about this? Okay. So I produce this 256 bit hash of this file. Now, do you think that there is another file in existence that has exactly that same hash? I mean, does one exist, period?
Statistically, probably not.
You have to remember though that there are infinitely many numbers in the universe. Like I just created like a whole bunch of random junk, and so this random junk is much longer than 256 bits. So I have infinitely many documents to select from, and all of these infinitely many documents have to be hashed down into 256 bits. So if the hash function is kind of uniform, if it really is pseudo-random, then it's likely that there probably is some other document that hashes down onto the exact same hash digest. So it's not realistic to ask for second preimages not to exist, because they just will. But what you want is for them to be infeasible to find. So you want the only practical way to find them is to do just about as much work as what you would have to do brute force, just trying every single, just keep trying documents until you find one that hashes to the same thing. And then you can model that as kind of a random process. So how long would you have to work to find a different document that hashed to the same value? Like about 2 to the 256 times. So nobody can do that. So if brute force is the only way to find a second preimage, then we're good. Okay. So what else? So there's this cool thing that we can do called a hash commitment. So this has lots of uses. Like you might have heard like of the Bitcoin Lightning Network. It makes a lot of use of hash commitments. But you can phrase it in terms of just simple things. Like let's say that we're going to play a game, and I'm going to say guess my favorite food. So somebody guess my favorite food.
Chinese food.
What did you say? Chinese food? And okay, so now I say no, it's not Chinese food. But what if I'm lying? What if it really is Chinese food, but then when you said Chinese food, I decided I didn't want you to win the game, so I just lied about what I thought in the first place. So we could fix this by having me hash the answer beforehand. So I could hash the thing that really is my favorite food. So let's say my favorite food really is Chinese food. And so this comes out to be some number, like OX, whatever, we don't care. I don't know. Let's just say it's that, okay? So now I can hand this over to you, and now I give this to you, and this is my commitment to what I don't tell you what my favorite food really is, but I commit to it being something. Okay, now when the game is over, let's say that you try 10 times and you didn't succeed or whatever, you can be like, okay, well, tell us what it is. Give me a pre-image of this. And so you want it to be the case that the only input that will make this output come out is Chinese food. So then you'll know that my favorite food really was Chinese food in the first place, and we can be confident that at least I'm not cheating at this game. So another example is basically the same kind of game is password hashing. Like if your password is swordfish, then a server doesn't actually store swordfish on the server. It stores the hash of this thing, which is 112a, etc. Okay, so what do these two games have in common? So you want to do this so that even if somebody knows this, they still can't log in as you, because it's not this that lets you log into TD Ameritrade. It's the pre-image of that. So what you want is for hash functions that you use for this purpose anyway, you want it to be impossible to find a pre-image. So this is not a second pre-image, this is just a pre-image. So let's write this down. So a pre-image attack is given some hash, given the hash of a particular thing, find X. So find the thing that is the pre-image of the hash. So desired security property of hash functions should be pre-image resistance, pre-image attack resistant. So it should be impossible for you to find the pre-image of a given hash. And that means impossible in practice, because obviously there is some pre-image. Okay. There's a historical example of this that's kind of interesting. Like, I don't know if you guys, if you took calculus with me, I'd probably at least mention that Newton and Leibniz argued over who invented calculus first. So while they were still corresponding, Newton wrote down the fundamental theorem of calculus, and he just said it really briefly, like the fluent or the fluxion is the whatever, and then he basically hashed that using like the 16th century or the 17th century version of hashing. And then he gave Leibniz the hash. And so he was able to establish, scientific priority later for the discovery without revealing anything about what he had discovered. Sometimes this kind of thing is also called a zero knowledge proof, which was apparently a common way to establish scientific priority back then. I always wondered if like, did Newton invent the hash commitment? But I think other people were doing the same thing. Okay. All right. So we've got two properties: second pre-image resistance and pre-image resistance. Okay. And so here's another case where pre-image resistance might be important. So suppose that here's Alice. Alice wants to send an encrypted message to Bob, and she not only wants confidentiality, she also wants some other cryptographic services too, like integrity, let's say. So one way to do that is to compute the ciphertext for whatever message she wants to send to Bob. So let's call that Y. And then she computes a signature for she signs with her public key, her private key, the hash of X, which is what she should do. Okay, and let's just suppose, for the sake of example, that she's using RSA to do signatures. So this will be h of x to her private exponent mod n if she's using the RSA signature algorithm. So she transmits the ciphertext, which she wants to remain private, and also the signature. This is a little bit dicey because the signature is not really designed not to reveal any information about the plain text. So you could argue that maybe this isn't the best idea for other reasons. But anyway, here's Mallory. So Mallory understands how the system works, and she also has access to the RSA public key, which is n, and then the public exponent e. So what Mallory knows that she can figure out what she doesn't know the message yet, but she knows that the hash of the message is just equal to the signature to the eth power mod n. So she's able to compute that. And now if Mallory is able to do a pre-image attack, she just runs this through her pre-image machine. And then she recovers X. And now she knows the secret message. That's another reason that you would want hash algorithms to be pre-image resistant. Okay. So there's this third thing that we're going to talk about called collision resistance. And this one is kind of more abstract and also stronger. So collision resistance means it is not feasible to produce x1 and x2 such that the hash of x1 is equal to the hash of x2. So if this did happen, this would be called a hash collision. Okay. All right. So the idea, I think, with this security property is just to do anything bad with collisions, you at least need to be able to do this. So if you have a hash function that is collision resistant, then it's going to be second preimage resistant also, because a second preimage would give you a hash collision. So it's just sort of a stronger property. And so to even begin doing anything bad, a person would at least need to be able to find some hash collision. So if you have a hash algorithm that is just collision resistant, so all these smart researchers around the world are trying to find collisions and they can't, then you can relax a little bit about somebody doing something like these signature tricks that we've been talking about. So collision resistance implies second preimage resistance. So to sum things up here, there are three just security features that you want well, sometimes you only need one or two of these features. It depends on the application, but in general, people want hash functions that have all three of these properties. One is preimage resistance. So given a hash, you can't find the thing that produced the hash. And you also want second preimage resistance. So second preimage resistance means that given an example, a document and a hash, you can't find a second document that hashes to the same value. And finally, you just want collision resistance. So this list is a little bit redundant because collision resistance implies second preimage resistance. Okay, all right. So they're actually, okay, so now even though we said that the collision resistance property was a little bit abstract, there you can sort of make up a thought experiment about how you could exploit exploit the ability to find collisions in a hash algorithm. So here's an example. You come up with some sort of good contract. So this is something that you could get a person or a server or something to solve, or like the book gives an example of like a purchase order, a seemingly legitimate purchase order that some kind of automatic validator really would sign. But just for the purposes of an experiment, could be like, I leave all my money to my children. Okay, so most people would sign a message like that. Okay, and there's also a bad contract, which benefits the attacker and which would not be signed by the authority if they knew what it was saying. And so this might say, I leave all my money to my, I don't know, what should it say? Cat's gardener. Let's say there's a nefarious gardener. My daughter really likes to watch Aristocats, where the lady leaves all of her money to her cats, and then the butler tries to kill them. Okay, so you have a good contract and you have a bad contract. So there are going to be lots of ways to modify these documents without there being an evident change. Like there are white space characters, for example. So maybe instead of one space or replace one space with two spaces, could capitalize some letters. I could add some punctuation. I could add in some carriage returns. And then, this might be like a Microsoft Word file or something. So there might be metadata that you could change that wouldn't affect the message that's presented to the viewer, but would change the hash because it would change the bit structure in the file. So you can modify this all kinds of different ways. Even if you only have like 100 places where you could make a change or not, that gives you 2 to the 100 documents. So this is sort of like no joke. You can make, with very few places to make changes, you can produce a huge variety of different documents. You can do the same thing down here. You can make 2 to the 100 variations. 2 to the 100 is not something that you could actually do, but I don't know. You could say 2 to the what's actually feasible? 2 to the 40. Down here you make 2 to the 40 variations. Oh, it just started raining at my house. Probably be raining at your house soon.
Yeah, it's raining. Very windy today.
So among all of these things, the hash is like a pseudo random function. So what you've got here is like 2 to the 40. You've got a table over here with 2 to the 40 entries. So that's the good contracts. And you've got another table over here with 2 to the 40 bad contracts. And each good contract can be compared with its hash against each bad contract. So there's tons and tons of comparisons here. There's lots and lots of ways that there could be a collision. So if you have a hash function that's not collision resistant, you might get lucky before long and find something on the good list that actually is a collision with something on the bad list. And in that case, you get your grandmother to sign, if this is the good column, or I guess you wouldn't do this to your grandmother. You would do this to the person who's employing you or whatever. So take this seemingly good contract and get them to sign that, and they say, okay, no problem. But what they actually sign is the hash, of course. Now you take out the bad document, which has the same hash, and then you replace, if this is like, X with some signature, here you replace it with X1 and the same signature. So you still can't produce the signature because you still need the private key to do that. But this will check out as valid because X1 has the same hash as X. And so you've just tricked the dupe or whatever into signing the bad contract. Okay, so this is the theoretical use of a hash function that doesn't, or abuse of a function that doesn't have collision resistance. So how many? Let's just say that we have a bunch of documents. Let's just start. What I want to introduce here is the birthday paradox. So maybe we can just introduce it the way it's normally presented. So how many people? We have 21 people in this room. So could everybody just chat their birthday? I'm gonna chat my birthday too. So just click on the chat icon, and I'm gonna type in my birthday. Everybody just type in their birthday. It's just the day of the year, not the year that you were born, just the month and the day. Okay. All right. So the birthday paradox is you have to have a lot fewer people than you might think in a room before two of them probably have the same birthday. So does anybody see a collision on this list? You'd have to be pretty smart to spot one. But there's a pretty, look, here's April 26th and April 27th. So that just missed by one. July 9th, November 7th, November 21st, June 26th. So so I don't see one, but there's close to a 50% chance that there would have been one. You can see we just barely missed. You know, we missed by 1 day in one case. So that's called the birthday paradox. It's surprisingly, so anyway, what's the question? So how many people let's say T is the number of people must come to a party before it becomes likely that some two people have the same birthday. So we'll work all this out using algebra and stuff. But just what we're going to do when we solve the problem is we're kind of just going to imagine that a birthday is a random number between 1 and 365. So a random number in the set 1 to 365. So another way to phrase the question is, how many times T do you have to draw a random number from this set before you get a repeat? So we can write a computer program. Well, anybody want to make a guess first? About how many times do you think we'll have to draw from this pot of 365 things before we have two that are the same?
I would guess like around 50. Because we got pretty close to one with just
Yeah,
20 people.
I should have asked this question before we did the experiment in class. So a lot of people would think like their intuition tells them that it should be about half the number of birthdays, which is way too much. And the answer I think turns out to be like 22 or something. It's like surprisingly few. So I wrote a computer program to do this, and if I can, are you guys? What are you?
We're
Sorry.
just looking at the.
Oh, you're just looking
people.
at that. Oh no, sorry. So anyway, I was writing this down. So the birthday paradox: how many people T must come to a party before it becomes likely that some two people have the same birthday? So you know, you're selecting a random number between 1 and 365. Okay. So let's go over to CoCalc. Can quickly write a program to model this situation. I think it's right here. Yeah, so here I have n. N is just the number of birthdays. So I had made it a really big number, but I'll just change this to 365. Okay. This is annoying. Okay, all right. So what I've done here is I have 356, oh gosh, sorry, I did 356, but the number of birthdays is 365. Look, I got a really nice output here. So the number of times it turns out I had to try was 18, and the square root of the number of birthdays is also about 18. So you can see where we're going with this here. But now let's try it with the right number. Okay. So here are 365 birthdays. So this is like people coming into a room, and every time they come into a room, they write down their birthday, which we're thinking of just a random number between 1 and 365. This actually goes between 0 and 364, but who cares? It's 365 possibilities. And then as soon as you get a repetition, you stop. So in practice, it took 24 tries this time. And the square root of 365 is about 19. If you keep doing this, there you can see that the number of tries and the square root of the number of birthdays is close. There's some variance because it's a random process. So sometimes it's more, sometimes it's less, but it's approximately the square root of the number of birthdays. And let's try this now with a bigger number, like 100,000 or something. So even here, there's some variation. Okay, all right. What have I done? Okay, so here now I made a graph, and if you care, like here's the you have what these numbers mean is, like, let's just consider this one. So this is saying that there are 3 people in a room. Then what is the probability that no 2 people have the same birthday? It's 99%. And say you have 1 person in a room. What's the probability that no 2 people have the same birthday? It's 100%. And by the time you get down to like 22 here, somewhere between 22 and 23, it starts to become more likely that some 2 people do have the same birthday. So when you have 22 people in a room, the probability that no 2 people have the same birthday is 52%. When you get to 23 people in a room, the probability that no 2 have the same birthday goes down to 49%. You can see that I'm doing something with a formula here. So let me just explain how that formula works. Okay. Oops. Oh, sorry. This thing is okay. Oh, that's annoying. All right. So let's make t in one column, and then in this other column, I'm going to write the probability of no collision for that value of t. Okay, so that means the probability that no 2 people have the same birthday. So if there's just 1 person in a room, there's nobody for them to collide with. So the probability of no collision is 100%. But now suppose a new person walks into the room. So now everything is fine as long as this person who just came in does not have the same birthday as the person who's already there. So that just means that they have one of 364 other birthdays. So the probability of that is 1 minus 1 over 365. So as long as you don't get really unlucky, there's this 1 in 365 chance that he has exactly the same birthday, but the probability that he doesn't is 1 minus 1 over 365. So then a third person walks in, and so now you're going to be okay. Obviously, you still need you need the first 2 not to collide, so you have to keep writing this part of the expression. But now this third person comes in, and now we're still okay as long as this third person doesn't have one of these 2 first birthdays that we've already crossed off. So the chances that that's true is 1 minus 2 over 365. And you can just keep going in this way, and here I'll just write t. So once t people get in the room, the probability that there's no collision is 1 times 1 minus 1 over 365 times 1 minus 2 over 365 times. And then what should I write here for the last term? 1 minus something over 365. So when t was equal to 3, that number was 2. And when t was equal to 2, that number is 1. So in general, it's t minus 1. Okay, so this is where this computer program comes from. So initially, p is 1. This NBD is the number of birthdays, which by default is 365. And t is the number of people that are in the room. So we go through. So what this does is it makes I take on the values I equals 0, 1, 2, up to, including t minus 1, but not t. Okay. So each time through, p is just times equals, this is like 1 minus I over 365. And so it's basically implementing this formula, and then it returns the result. Okay, so we'll clear all that and close this. So you can plot what happens. So here on the y-axis, this is the probability of no collision, and then on the x-axis is the number of people. And so right here is where there's a 50% chance of collision, and we know that the number of people there is 23. But it's really dropping fast there, and by the time you get to 40 people or 60 people, if you have 60 people in a room, the chances that there's no collision of birthdays is essentially 0. Okay, so what does this have to do with hash functions? So hash functions are kind of like birthdays. So you could say the hash of a document is its birthday. Okay. So now instead of having 365 birthdays, there are 2 to the n birthdays, 2 to the n possible birthdays. Where n is the number of bits in the hash. So, you know, if this is SHA-256, then it's 2 to the 256 possible birthdays. So it's the number of bits in the hash digest. So now you can ask yourself a question about a hash function that's just the same as the question about birthdays. So how many files or messages? So how many messages x1, x2, x3, blah, 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 up to xt before the probability of a collision exceeds a half, or however much, however likely you want it to be. It turns out that the number of messages t, if you want the probability of a collision to be greater than a half, it's almost the same number of messages as if you want there to be like a 90% chance or a 99% chance. You know, whether this is 9 out of 10 or 99 out of 100, it turns out not to affect the number of documents that you need very much. So you can, I will quantify that, I guess. And so we're going to derive the answer now. Let me come back to my notebook. Is there anything else interesting in this document? I don't think so. No. So we'll just come back to the notebook here. All right, and now let's do this derivation. So this is sort of like what we were doing last time. So now the probability of no collision with T documents is equal to 1 times 1 minus 1 over 2 to the n. So n is the number of bits in the hash, times 1 minus 2 over 2 to the n, times 1 minus t minus 1 over 2 to the n. So 2 to the n is a huge number, and for any t that we're practically going to be able to explore, the ratio of t to 2 to the n is going to be like essentially 0. So what we want to do is, if you were just going to try to solve it, you would try to solve this equation for t. But if you multiply this out, you're gonna get some big mess, and so this equation is too hard to solve. So instead of just trying to solve that equation directly, we're gonna use some tricks. And one trick is we're gonna use instead of using this, we're gonna use exponential function. And the way you can do this is, if you remember from Calculus 1, if you look at e to the minus x, so here's e to the minus x, and here's a plot. The linear approximation at 0 here, is going to be the tangent line there. And it turns out that the tangent line, which is the linear approximation of this function near 0, is the line y equals 1 minus x. And so what that means is when x is near 0, so x is approximately 0, and all of these things are approximately 0. That's approximately 0, that's approximately 0, that's approximately 0. When x is approximately 0, 1 minus x is approximately the same thing as e to the minus x. So we can rewrite this as, well, it's approximately equal to. Okay. Not exactly equal to, it's approximately equal to, and I'll just leave off this 1 too. This is like e to the minus 1. Well, before I do that, let me write this thing in product notation. So this is the same thing as the big product as I goes from 1 to t minus 1 of 1 minus I over 2 to the n. Okay, and we're going to replace each one of these with, so this is going to become the product is approximately equal to, the product as I goes from 1 to t minus 1 of e to the minus I over 2 to the n. Okay, right. So that's actually much nicer because if you have like, you know, e cubed times e to the 4th, this becomes e to the 3 plus 4. So instead of having a big product of the bases, you're just going to have a sum in the exponent. So this is the same thing as e to the sum of minus I over 2 to the n. And this is as I goes from 1 to t to the n minus 1. This is probably going to run over time, so if you have to leave, it's okay. You can just watch the recording later. But I'm just going to keep working here. So this is the same thing as e to the minus I over 2 to the n. And I can actually factor out the 2 to the n because that doesn't depend on the counter at all. So this is minus 1 over 2 to the n times the sum of the i's. And you might know either from 204 or from calculus 1 that there's a formula for this, the sum of the first t minus 1 digits. And I'm just going to write that in. So this is e to the minus 1 over 2n. And so this is t minus 1 times t divided by 2. All right. So just for this, the book sets this equal to 1 minus lambda or something, but let me just make it easy. Let's just set this equal to 1/2 and solve for t. So remember, this is the probability of no collision, right? And if you want to do the full detailed version with lambda, you can just read that in the textbook. Okay, so how big does t need to be before the probability of no collision is down to 1/2? You know, it starts out at 1, and then the bigger t gets, the smaller it gets. So we're asking, how many documents do we need to get before the probability of no collision drops below 1/2? In which case, it's going to be more likely than not that we get a hash collision. So you just apply natural log to both sides, and you get minus 1 over 2 to the n, t minus 1 times t over 2 is equal to natural log of 1/2. Then a nice way to get rid of that negative, you can get rid of that negative sign and just have this be 1 over 2 to the n times t minus 1 times t over 2. This negative sign can come over here and apply to the exponent here. You know, 1/2 is 2 to the minus 1. And when you put a negative next to a log, it can go inside and be in the exponent. So minus 1 times minus 1 just becomes 1. So this is equal to natural log of 2. And remember what we're trying to do here is solve for t. So on the left, we have 1 over 2 to the n minus 1. Oh, sorry, n plus 1. I just combined this 2 and that 2 to make n plus 1, 2's. And now we just have t minus 1. T is equal to natural log of 2. We'll start again up here. T minus 1 times t. is equal to 2 to the n plus 1 times natural log of 2. Now we're going to cheat again. So we have, we could solve this as a quadratic equation. It wouldn't be super hard. But just so we can get like a better intuition, let's just replace this with t squared. It's pretty close to t squared. I mean, t is probably some pretty big number, so t minus 1 is going to be about the same, and so that's just roughly t squared. So t squared is equal to 2 to the n plus 1, natural log of 2. And now we can take the square root of both sides, and I'm going to ignore the negative square root because we don't care about, negative number of documents. So n plus 1 times natural log of 2. Okay, so finally, this is 2 to the n plus 1 over 2 times the square root of natural log of 2. Okay, so, and there's this is still a little bit, we have this funny constant here, the square root of 2, which is not very big. You could actually quickly see what that is. I think it's something just a little bit bigger than 1. So the important thing is here, this is roughly the same as just the square root of 2 to the n. So this is the square root of the number of possible hashes or birthdays. So this is, you can think of this as the square root of the number of possible hashes, or the square root of the number of possible birthdays. So that's why those numbers were the same when I did the experiment on CoCalc, and it's also, this constant here explains why the square root of the number of birthdays was always just a little bit too small, because I was leaving out this constant here. And I was also leaving out this this plus 1. But it's close enough to think here just that the number of documents you have to have before there's a collision is the square root of the number of hashes. Okay, so that's why there cannot be an 80-bit hash function. So if there were an 80-bit hash function, 80 bits is we're thinking of that in this class anyway, as a sufficient level of security. So if you had an 80-bit hash, there would be 2 to the 80 possible hashes. But then you would only need 2 to the 40 documents before you got a collision. But 2 to the 40 is totally doable. And so if you want a hash function that's collision resistant, you have to have a hash function that is at least 160-bit hash. And RipeMD, I think, actually realizes this minimum. I think RipeMD is a 160-bit hash. And the reason is that if you have a 160-bit hash, you can still find a collision with 2 to the 80 space and time. 2 to the 80 is, we're thinking of that as being, for now, it's an implausible amount of work. So, but anyway, this kind of illustrates something that's true in cryptography in several different places, which is if you want the security level to be S, you need like a number of bits that's actually like 2S. So if you want a, that's why we have SHA-256 instead of SHA-128. So SHA-256 has a 256-bit digest, but it only has a security level of 128 bits. Anyway, so that seems like a good place to stop. Anybody have any questions? Okay, did anybody find a hash collision on our birthdays?
I don't think so.
Oh, May 11th? Does May 11th work? So actually, so whose birthday is May 11th?
Oh, it was mine. It's twice. It's not twice on there.
Oh, okay, so is it really?
People are saying 26. June 26th.
Okay. You just wrote it twice. Oh, June 26th though. So whose birthdays are June 26th? Aiden and who else's birthdays?
Raymond.
And Raymond. Okay, awesome. Oh yeah, Raymond can't talk. So awesome. So I do this every semester, and usually I get unlucky, but I got lucky this semester. So with 22 or so people, we got a birthday collision. So that's like a party trick that you can do when social distancing is over and you're in the same room with 23 different people, which might be a while.
Just go around to every person. What's your